and then we
Yeah, it's
excellent.
starting.
Good. So there we go. Jared.
Jared.
Yeah, okay. Can you see my screen?
Yeah.
Yes.
Okay. So I will briefly introduce my subject, like always, and I will show you my result on modeling distributed seismicity using innovative approaches. So first of all, what we need to explain is how to model hazard of a region. Okay, so we will take an area, and we have two topologies possible of sources. The first one is fault. So the seismic occurrence is characterized by slip rate. And in other case, if you don't have any information about fault sources, what you will have is the past seismicity. And so this is characterized by the second typology, which is distributed seismicity. So in the current way of modeling area sources, so let's take a probabilistic seismic hazard model, such as OpenQuake or this kind of software, okay? So this software will do, so an area, you take an area, you have a site and you want to have the hazard at this site, okay? So what the software will discretize this area into different cells and with the same length and then width, okay? And at every center of the cells, it will set the centroid of the rupture. So it will do that for every cell, okay? And because also we don't know about, like I said, we don't know about the position and the orientation of fault, it will set like different orientation possible in this area, and it will set all the faults in every center of the cell, okay? Which means that here, we consider that if we take, I don't know, a magnitude of about 7.5, it will set all the rupture of 7.5 at every position of the center of the cell, okay? So it will do that for this direction, this orientation. It will do that also for this orientation. And at the end, what it will do to compute the hazard is just like to do that. What we will have, sorry, is the mean hazard curve, which is the annual probability of accident in Y and the peak ground acceleration in X. So we compute the mean hazard curve of this pattern. So like I said, the problem is that we can have a probability, we can have a magnitude of 7.5 everywhere in the region. So this is not really realistic, okay? But if we take, like, I don't know, let's take a period of interest of investigation time of, I don't know, like billions of years, okay? We will have a possibility that, okay, we will have this fault that, well, a rupture that can happen everywhere in the region because we take a very long period of time. But instead, if we take a period of time that is very close, like I don't know, 50 years, considering that we will have a rupture at every position of this area is unrealistic. And what we want to do is to not use this type of model to compute the hazard, okay? So in our new approach of modeling distributed seismicity, especially here area sources, so we'll do exactly the same. How can we model it? So we will take again an area, okay? You will have a site in the middle. You can put the site everywhere, but it's just in this case we put it in the middle, okay? And what we want to do is to see the spatial variability and the time variability. So to see the spatial variability, this is very simple. What we need to do is for a period of interest, such as, I don't know, like I said, 50 years, okay? Using a magnitude frequency distribution where you will set that, well, you need to use one or two equations, okay, to get the number of earthquakes for this period of interest, okay? But, okay, you will set that for 50 years, you have, for magnitude 5, I don't know, 10 ruptures. For 10 ruptures, you will set the rupture aleatory in this area, okay? That's what we do here. And we will do a lot of simulation where we will put the orientation and the position of the fault totally randomly in the area. And we will do that for a lot of simulation. So which means that for every simulation, we will not have the same position of fault and orientation of fault. In another case, I will not enter into detail here, but what we do also is, like I said, to see the variability in time. So here we have the variability in space, because the faults are not set at the same position, and in time, because when we compute the number of ruptures for a period of interest that we want, okay, we will use a Poisson distribution, which means that for every simulation, I will not have the same number of earthquakes for every simulation, okay? So now we have that, and for every simulation, we will compute the hazard curve, okay, of this site, which means that for every simulation, I will not have the same shape, the same shape of the hazard cube. The hazard cube will not have the same value. And then if I combine all these hazard curves, what I will have at the end is this kind of variability here, okay? You can have the variability here. We will see just after, okay? But here will be the epistemic variability in time and in space. So what we did is to create a stochastic simulation of rupture pattern, which means like for every simulation we don't have the same pattern of fault position, etc. So as you can see here, this is a full aleatory uncertainty model. So this is the model that we currently have, like the model of PSHA software. Okay. So as you can see, there is all the faults that are set in the middle of each cell, discretized cells, okay? And in our case, this is a sample modelization here, okay? But as you can see, at every cell, you don't have every position possible, and you don't have all the fault at every cell. Okay, so now we have our model, and we also have the model of a software, such as OpenQuake, okay? And what we want to do is to compare these two results. And to compare these two results, we took the model of ESN 1020, which is the European Seismic Hazard Model, which is of 2020, sorry, which is the result of PSHA carried out for the Euro-Mediterranean region, okay? And for this case, we take the model of ESH20, okay? We take our model and we try to see the difference between these two. So in the ESH20, they made some zonation, okay, of area. And because we want to compare these two results, we take a random, not a random city, okay? But we take two cases. For the first one is a city that have a low seismicity, okay? Such as Stockholm. So as you can see, we take all this area into consideration for our calculation. Why? Because we take an integration distance of 300 kilometers around the site, and for every rupture that are just after 300 kilometers, it will not be counted because we don't want to compute for every rupture in the world. Okay, so this is why we take an integration distance of 300 kilometers. And so in these 300 kilometers, we have six areas that are included. And we do exactly the same, but for now, for another region, another city, here is L'Aquila. And so we also take 300 kilometers of an integration distance, sorry, of 300 kilometers around the site. And you will have here 25 areas that are included. Okay. So I'll talk to you about the variability in time. Because I said that for every simulation, you will not have the same number of ruptures, okay? So in this case, in blue, you have the magnitude frequency distribution for the area. So this is the 6th area of Stockholm, okay? So in blue, you have the magnitude frequency distribution, okay, for this area, the 159, for this one, for this one, for this one, okay? And as you can see, the magnitude frequency distribution is not the same because the seismicity is not the same in every region. So what we do is we create 10,000 simulation in this case. And what we want to do is to see if we take the average of the MFD, because I told you that in all the simulations, sorry, for each simulation, I will not have the same number of earthquakes. So the magnitude frequency distribution will be not the same, okay? Like for one simulation, it could be like this one with one or something like that. I don't know, okay? But if we take the average of the MFD of the 10,000 simulation, what you will have at the end is this orange curve. Okay, so for every area. And as you can see in this case, if I only take 10,000 simulation, okay, for a low number of earthquakes, the average magnitude frequency distribution of all the simulation will not fit as good as the actual magnitude frequency distribution of the area, which means that we don't have the same information. So in this case, what we need to do is just to use a lot more, much more simulation, and I already did that, and these two curves fit well. Okay. So in this case, I didn't tell you about what I did, but I just take a period of interest of about 50 years. So I consider all the rupture that can happen in this area in 50 years, okay? And so if we do like 10,000 simulation, what we will have is 500,000 years of seismicity that is modeled here for every area. So it was for the variability in time. And now if we look at the variability in space, but also in time, okay, because here we did it for time and the spatial variability. So this time is for L'Aquila. So here we made 910 simulation, okay? And we also take a period of interest of 50 years. And we have like the integration distance of 300 kilometers. So this is the stochastic rupture pattern for only one simulation. So as you know, you can see different rupture that are set everywhere in this region. Okay, and for every region, I will try to see the contribution of each region of the hazard at L'Aquila, which means that for each region, I will have for every simulation another curve. I will have another curve. Okay, so like this region, for this region, for one simulation, there is a possibility that I have this other curve. You know, so as you can see, a very low probability of occurrence of accident, sorry, and an intensity measure level that is very low. And you can also have a probability for another simulation that for this region, the probability of accidents will be very high, and the intensity measure level also will be very high. So in red, you have the mid-hazard curve of all this simulation, and as you may expect, so the variability that you will have for all this simulation is very high. So this is the actual variability. Okay, and so you can do that for every areas, and this one is an area just right there, so it's very far from the site, and so the probability occurrence, the variability of the probability occurrence will be lower than this one. Okay. So thank you. I did not know. I didn't go into detail on the way of how I did that, but it's just like to show you a little bit about the result that I have for now, and yeah, thank you.
Thanks, Gerard. Questions or I don't know, comments? Anybody? Yeah, so well, I mean, I can say you won, Gerard. it's not clear. Yeah, on this slide, I mean, the sub areas that you show that you've given names to.
Yeah.
I mean,
This,
are basically small patches or small areas all over the region, or is that right? But I mean, how small are
yeah.
they?
Yeah,
Clear.
I didn't put the area zonation, but the 351
Yeah.
is this one.
Oh, okay.
Okay,
Right.
so
Okay.
this,
So there are sub areas. Yeah.
yeah, that's right. Yeah.
And so the variability that you show in the end for these ones are, I mean, they're both due to the Poisson nature of the occurrence, and they are also due to the I
The
don't know,
position and
the
the orientation
position
of the
and the
boat.
orientation. Yeah.
Yeah, sure.
Yeah. I mean, the orientation are resolved as well. I mean, it's like it is like using a dislocation code then.
No, we took like the same orientation of ESHM 20, exactly.
Okay.
So yeah, you have like different orientation, and we took on this different orientation the possibility, different possibility.
But I mean, there are different accelerations for all the various geometries. Is that right? Yeah.
Yeah, I think so.
Oh, okay. Okay, good. So, any other questions? So what are your immediate plans for the next weeks?
I am currently writing like a report to share with all the supervisor
Okay.
about the methodology, just to be totally clear. And
Yep, that's a good idea.
so I will send it to you, to Céline as well, to Oona as well. So I just need Marco to review it, and I will send it to you.
Yeah, good.
And after that, what we wanted to do is to, because here we take like a purely stochastic method, which means that we set the position of the fault, like the bigger fault. It could happen like everywhere in the region, but in this case, this is not very realistic. So what we wanted to do is to constrain this biggest fault to a region where we have a possibility to have this rupture. Okay, so
Mhm. Okay, so you need specific expertise for
yeah,
this. Okay.
like your expertise.
Yeah. Okay, good. It's time to move on, I guess, unless there are questions by anybody. So it's John's turn now. So John, you're the first to you're the first to go around the clock. So it's your second time now.
Exactly.
So yeah, it's that's for, I mean, for all you guys, whenever you present again, yeah, don't hesitate. It's good to show, to give one slide about what you were showing the last time you presented, and then and go on and show what you've done in the meantime. It's really like in the meantime and in a very near future that is of interest to everybody. So go ahead, John.
So are you seeing now my stream?
Yes.
So perfect. So let me hit. Okay. So hello everyone. So this is my update. Actually, this is I consider my first presentation, my first update, because the last time when I did it in November, actually I hadn't officially started my PhD. So this is my project. So this is the earthquake timing in complex fault zone, new approaches in paleoseismology. So I prepare a really general presentation, and I apologize if a kind of repetition, but I would like to highlight what I'm going to show you. So have here more or less that what we are going to see in the presentation. Again, a bit about the goals of my PhD. The methodology that I'm undertaking regarding the reference review, also the information, courses, and topic that I have the target to learn, some information again regarding hyperspectral imagery.
I am not seeing it. Your slide is not changing.
It's not changing?
No,
Okay, let me see it again. Sorry.
All right. Yeah.
Maybe you should put it on on the full screen.
Yeah.
Exactly. Yeah, I will go immediately. So.
And John, please don't be too long.
No worries.
Kind of
No,
worried
no, no.
that you might be.
Okay.
Okay.
Oh my goodness. So, so I have the same. I have a problem here to. Are you seeing now my presentation? In the presentation mode.
No, no, but I mean, if you go through, on the left panel, you go through the slides, and that.
How about in this way? Is okay?
Oh, yeah. Well, try to move on to the next slide. Okay, good.
Okay. So I have to go really fast here. So my idea is to show the general things that I've been doing during this month. So the main purpose of my PhD is about paleoseismology. So this is really important in terms of seismic hazard assessment because actually we can expand our seismic catalog. We can also identify active faults, and also by understanding the frequency and period of past earthquake, we can know a lot about foul behavior and interaction. So with that in mind, I would like to formulate my research question that actually is related to enhance the precision of locating earthquake chronology event horizons and decrease the uncertainties in paleoseismology by integrating new techniques. I would like to say again the example of the Lama de Murcia fault. Here we are in the Eastern Betic shear zone. It's a transpressive tectonic setting where we have some historical earthquake. For instance, here we have in Lorca, in Torrevieja, in Almería, earthquake that happened some centuries ago, with magnitudes ranging between 5 and 6.6. And the last one actually was in 2011 here in Lorca. So here we have the Lama de Murcia fault that is about 90 kilometers length. And this fault actually has different branches regarding to its deformation. Several studies has been done there by the University of Barcelona and the RISNA group. So here we see with the yellow stars some of the paleoseismological sites. So the idea is to focus here in the Saltador because this is one of my study areas. So here we see on the right all the trenches that have been opened. So they have a 3D, the perfect place for a 3D foul understanding. So in the trench number 6, here we see in the bottom we see the interpretation, the paleoseismological interpretation, and we have if we can have a look here in the faults number 5 and number 4, we see that the formation actually is concentrating in the bottom layers. But if we just go to the top, and to the closer view, we can see actually that this interpretation, I have an animation here, so I will put it away. So the interpretation actually just went just to the layer number C and number B. So the deformation just concentrated below. But how about if we can have more events deformation on the surface, so it can change the leap rate. In the same way, here we have in the fault rock in the Apennines, we can see different patches in the fault rock that probably are related to weathering, but are they also related to a seismic events? So the idea is to integrate different novel techniques, not only the hyperspectral imagery, to trying to understand and to better interpret this kind of outcrops and deformation. So what I've been doing so far is just collecting a lot of bibliography. I using Mendeley mainly, and also this kind of app to connect and also to trace the main findings of my topic. I use some Excel document just to organize to better organize my information. I've been focused my review about hyperspectral and multispectral data. So what I've been doing actually is just trying to understand the origin of this technique. I think our human eyes is quite limited just to the visual spectrum. I have here just the information, as you can see, the visual range of the wavelength is really limited. So we are going to use the visible the near infrared, and also some part of the shortwave infrared. So about 400 nanometers to about 2,500. That is the range of the most of the common cameras nowadays are processing. So the idea actually is to, I think the advantage of this technique is that we can have, instead of just bands or a few bands of the multispectral imagery, we can have 100 of bands, and we can have a spectrum that is related actually to the mineralogy and is really sensitive to moisture, to grain size, and also to the incidence of light and the position of the grain. And that's why it's kind of suitable for paleoseismological assessment. Some study has been done before. For instance, we have here some paleoseismology course by Ragona. We have here the change of the colors. These false colors actually related to hyperspectral imagery that can be easily traced and identify the deformation. A lot of machine learning advance also have been done in this field. Here we have the study of Maurice Kears, where we can actually trace automatically some geological mapping. So for the tools actually that are used in hyperspectral imagery, we have these cameras. Actually, these cameras are not only the camera, there are a lot of behind actually. There are this kind of calibration, the tripod actually is quite expensive. We have another matter regarding the use of the camera, for instance, how far we are from the target outcrop, how is the moisture, how is the shading. Nowadays, actually, they are using also drones to combine with the structure from motion technology. Here on the right, we have just an example of the application of this technique in Greenland for a mining purposes. You can see here the true color image, and they combine the 3D hyperspectral imagery into a point cloud photogrammetric tools, and also some algorithm just to enhance the view if they want to see the contribution of hydromineralogy, also carbonate mineralogy. So we want to take advantage of that, doing this kind of things, for instance, in this paleoseismic trends by the study of Maurice Kirsch, where we can have this hyperspectral imagery into photogrammetric tools. So in terms of processing, a lot of software had been used for managing the hyperspectral data. Normally, it's used the Hypercube and Envy, but nowadays a lot of package and tools by Python are really common. I'm learning a bit about it, especially the highlight. I'm not an expert on that, so this is my target, and also about the basics of photogrammetric and so on. So in terms of my field, this is the Lama de Murcia Fault. We went to the southwest to the Palomares Fault. This is another strike slip fault. I was supporting the PhD of Julia Molins from the University of Barcelona as well. There we were just collecting some quaternary samples for dating, identifying some interesting outflows for the application of the camera. So here we see actually one of the outcrops. We can see here just the Mars just above, and all the alluvial deformed sediments on the top. We see here that we can trace in some of the areas easily the faults, but in some areas actually we couldn't recognize how are the faults reaching the surface. So in this area actually the camera will be also really useful. Also in this picture, we went to visit another area where we can have more recent sediments where the formation actually was not so clear. We identifying some evidence on liquefaction that actually can be related to just sediment charts, and also to an historical earthquake that happened in the town of Vera in the 15 something. So for sure the camera will be really useful here. We also visit other beautiful outcrops. Apart from my happiness face, actually here in this stripe slip fault and the vertical deformation, we can see in red just the easy correlation of the deformation, but in yellow actually just on the surface the faults are not so clearly seen. So in this area, the camera also will be really useful. And we have also here the contribution of the weathering and the paleogenetic soils formation. That's why it's kind of tricky sometimes. Here the same, we have the fractures that goes and easily traced in the Mars, but in this reddish layer actually is not so clearly seen. So I also went to the Camp Fall, this totally different area just close to Barcelona toward the south. We have an extensional area, mainly normal faulting, and we have there some escarpments. And I also was supporting Mark Collet, PhD. He's trying to understand and to find the relationship between tectonic activity and gravitational processes and also cars. He's doing some geophysical methods, so I was learning a bit from that and the possible use into paleoseismology. They also have open trenches, so it's perfect place to understand the geology. In terms of the workshops and events, I'm going to attend next April to a spectroscopy workshop in Valencia. We submit two short abstract for the Geological Congress in Spain that is going to be on July. The one about my master thesis and the second one about the research proposal of my PhD. I also planning to go to these two events, but I have pending what I'm going to present. So I still have the time to discuss with my supervisor about it. Just regarding my current and coming tasks, I want to show you this timeline. So in April, I am going again to help in the trenching campaign of Mark in the Camp Faults. I'm going to be in the workshops and the Astra preparation, and probably, but still not sure. I'm enjoying a campaign in Italy within the Ceres team with Magali, Lucilla, and Najaret. I'm still not sure about it because we'll be kind of busy. In May, I'm going to help again to the Palomares Fall campaign of Julia Molins. And I think the most important is that I'm going to have the first time of the use of the hyperspectral camera. Actually, my partner advisor, Maurice Kirsch, he has another project here in Spain, so he's coming at the beginning of May, and we want to take advantage of his arrival actually to go to one of the open trenches in the Alhama de Murcia Fall in the Saltador. This trench is open already, so we have to clean it again. We want to do reinterpretation and also working with this LiDAR, working the geomorphology and the photo interpretation to try to compare all the work that has been done. And that's it. I think that's all from my side. Thank you very much.
Thanks, John. That's very complete. Very nice. So I don't know if you guys have any question. Myself, I mean, it's I understood everything. So even though it's not my specialty, no, it was very clear and very thorough. But I don't know if anybody has any question for John.
Thank you anyway.
All right. Okay. So in any case, well, good luck with the coming weeks, and Moss seems to be quite busy. Okay, so now we can turn on to both Céline and Oona. So I don't know who's going to start.
I'm going to start.
All right. Okay. So the deterministic approach first.
Yes.
Good.
you-
All right.
Partager. Can you see the slide?
Not yet.
Not yet.
Yes, we can.
Yes, you can, but I can't. So I don't know what the problem is. I don't see it anymore.
All right.
Why is it like that? It's down here somewhere. It disappeared. Well, and
Can
it's in
It's not in diaporama mode
it's
yet.
not in diaporama mode. Okay, let me put it in diaporama mode, and let's see if I can do it. Still not in diaporama. Okay. Still not in panorama mode.
No, not yet.
Okay, here we
Yeah.
go.
Okay.
All
So
right.
we can see the next slide every time, yeah, but it's okay, you know, we can deal with this. Ouais, ça fait tout, tiens, Oona, ça fait toujours avec, tu sais, la diapo suivante, et puis si tu as des notes écrites là en bas, ça montre ça en fait. We can't hear you anymore, Oona, in any case.
Okay. Now you can hear me?
Yes, we can.
And
Yeah, it's still not in diaporama mode.
well,
But I mean, if it's okay. I mean, we can keep it like
Yeah.
this. That's okay with you. And that's again the same you know type of you know mode as I mentioned. You know, we can see your next slide. Oh yeah, you're good. No, you can do that.
it's okay.
Sure.
It's not ideal, but
No, it's okay. Now we can follow. Yeah, we can
okay. Anyway, so sorry
Right.
for this, and just wanted to introduce you the fact that we've prepared two parts to this presentation. The first one, it's mainly dedicated to an example of deterministic seismic hazard, and then Céline will go on with the probabilistic approach. And the reason to do the two together is just because probabilistic approach is probably everything that you will ever hear about, because today people basically practice only probabilistic approaches, but deterministic approaches remain something that is done especially in the nuclear industry and especially in France. And so it's kind of interesting to go through this to this approach. This approach, you know, has different, take on different forms in different countries. The main issue we were trying to cover at IRSN was concerning the propagation of uncertainties in DSHA. It's formally done in probabilistic hazard assessment, but it's not formally done in DSHA. So this is what I'm going to try to present to you. At IRSN, it's an institute that is mainly a scientific support for the French Nuclear Safety Authority. And so we have both the mission of expertise, where we check that nuclear operators' safety reports comply with the regulation, but we also have a research aspect in our daily life in various fields related to nuclear safety. And so the institute is made up of 1,700 employees, so we cover very different aspects, but 10 people are dedicated to the seismic risks aspects, and it's called the Bersin. And so what we do at Bersin is we try to define seismogenic sources, characterize their activity. We model strong ground motion and site effects. We compute seismic hazard related to ground motion, but also to surface rupture. And then we provide the seismic motion to the engineers, that then they go on and hopefully demonstrate that the nuclear power plants will resist to the next earthquake when it comes. So the DSHA methodology is pretty much the same as the PSHA. We need to define the same things. We need to define geometry of seismic sources. We need to identify scenario earthquakes. This is the biggest difference with PSHA. We only identify the biggest scenarios earthquake of interest to the site. And then we need to estimate magnitudes and depth of these scenario earthquakes And as you will see, we are mainly involved with historical events. And so we need to develop intensity models to try to estimate these magnitudes. And finally, we do need also ground motion models, just like PSHA. So defining geometry of seismic sources, especially in low seismicity regions, it's a big challenge. We need to look for geological, geophysical, and seismological homogeneity to some extent, because we consider each zone as being a zone where the occurrence of earthquake can be supposed to be uniform. So to do this, we rely on a combination of geologic, kinematic, and geophysical data. So here I'm showing you an example from the Belgian colleagues that are doing very similar approaches as we do in France with very nice pictures. So if we take an example where we have identified a site and the two sources that we are going to be concerned with for this site, and then you see that we have identified two earthquakes. One earthquake in site 1, and that occurs within the site region, and then another earthquake that occurs 20 kilometers away. So how did we identify these two sources? Is because they have the biggest effect in terms of intensity at the site. And how did we do this? Very simple. We take the intensity that we know, the macroseismic intensity that we know from these different earthquakes. Here you have an example of a 1580 earthquake, whereby each circle represents the intensity that we could evaluate from the archives. Okay, so maybe you are familiar with intensities, but just as a reminder, macroseismic intensities are based on a classification of the severity of ground shaking deduced from a statistical analysis of felt or observed effects. And when we get up to the damage level, then we are about in intensity 7 in the red circles here. So here you see the epicenter of this event is actually somewhere between England and France, in the middle of the channel. So this kind of information we have for many events dating all the way back to 1,000 years ago in the database in France. And so this is what we have for these two events. We have their intensity, the way they were felt in different villages around the epicenter. And what we do is we take that intensity field, we somehow deduce what we call the isoseismals of the event, which are trying to describe equal intensity felt around the epicenter. And then the deterministic action here is to say, well, now let's consider that this event is in a seismotectonic zone with equal potential, so it can also happen very close to the site. So the closest point to the site is 20 kilometers. And this is how we define the scenario for the scenario 1. So this earthquake, considered in a deterministic scenario, will induce an intensity 7 if it were to occur at this site. Now, if we take the other event and we do the same thing, we try to draw isoseismals. In this case, it comes straight underneath the site. So you understand that for this particular event that comes straight underneath the site, it's going to be very important to evaluate not only the magnitude of the event, but also the depth, which is a bit challenging given the data that we have. So here we have these two events, and now we need to estimate the magnitude and the depth. So to compute the ground motion, eventually, we need these two parameters. As you know, the ground motion depends on the magnitude of the sources, their depth, the propagation, and of course, the site effects at the end. To do this, we have to develop what we call intensity-based earthquake magnitude estimates, which of course are uncertain, and at each step there are expert decisions to make. So I'm presenting you one procedure, but beware that there are many different procedures that will lead to different evaluations of the magnitude, of course. So what we developed is a two-step procedure, whereby in the first step, we estimate intensity attenuation and the associated uncertainty from microseismic data. And then we calibrate each intensity model using earthquakes, for which we have both instrumental and microseismic data. Because we continue to feed this database even today with intensity data for this purpose, to be able to calibrate and update our calibrations as new events happen in France. So what you see on the left is the CIS-France database of historical seismicity. And you see we do have earthquakes in France, although we don't have them as often as in Italy. But there are enough earthquakes to worry about. And so what we do is we choose among these earthquakes the ones that have a sufficient number of macroseismic intensity data to be able to estimate the average attenuation of intensity with distance. And the formulation we chose is this one. There are other ones in the nature. It's the Kovalevsky and Sponauer formulation, which allows us to somehow try to estimate how the intensity diminishes as we go away from the epicenter. So an example of expert decision is right here. There are two ways in that one can describe intensity attenuation with distance. You either do the mean of each intensity level, you look for the mean distance, or for each distance, you look for the mean average. So the green one is it's called distance binning, and the red one is called intensity binning. And as you can see, depending on which way you do this averaging, you will get a different shape, especially at higher distances. So we decided that the best and most appropriate way of modeling intensity attenuation with distance was the red one, called the intensity binning, because we believe that all the green diamonds are actually showing anomalies at higher level intensities because of side effects being predominant and more represented at higher distances. So to convince you that these two ways of binning can lead to different, very important differences in intensity attenuation, we have set up a series of tests and inversion strategies to try to constrain this intensity attenuation using these two E average and R average distances. So what you see here is that we have selected different types of events depending on a couple of criteria. We have different types of a priori information and different types of inversion schemes using regional and national criteria. I'm not going to go into the details. The important thing is that no matter what you do, you will come up with very uncertain results. And here specifically, depending on the distance or intensity binning, you will get distinct slopes. So if you ever have to deal with intensity attenuations, beware that there are highly implications behind the modeling. So we will go on just with the R average approach, and we'll drop the E average approach, and consider the entire distribution that comes out of this exploration of the different parameters. So in the second step, we select a different set of events which have sufficient macroseismic intensity data but also well-known instrumental magnitude and depth events to estimate the magnitude parameters C1 and C2. And finding reliable magnitudes, instrumental magnitudes with reliable depths is not an easy task, but one has to be very severe about the criteria used in selecting these calibration events. So again, we go through, we have our distribution of beta values with their weights. And then again, we test different starting depths. And we have to do quite a few hypotheses about the depths that we can allow in these inversion schemes, unfortunately. And then, of course, depending on how wide an area you use in terms of calibration events, you will get a different response. Here in France, we don't have a lot of high magnitude events, so we went to Italy to try to grab some higher magnitude events in order to be able to predict the magnitude of higher intensity events. And so here, what I'm showing is the result, where you have in the bottom the instrumental magnitude, and on the y-axis the macroseismic magnitude that we could compute using this two-step procedure. So in the end, we don't have just a number as usual in the catalog, but we have a probability density function in the magnitude depth space. That gives us a little estimate, appreciation of how well we know these magnitudes and depths of these historical earthquakes. So there is a paper that has been published recently that you can consult if you're interested in the details of this procedure. But I mean, if you want, we can discuss it now if there is interest. Otherwise, I'll just keep on going to go to the end of this exercise. We now have magnitude and depth and uncertainties associated. And we have the distance to the site of our earthquake scenarios. So we're ready to compute our hazard given a ground motion. So I don't know how many of you have already looked at the response spectra, but for seismologists, ground motion is a seismogram, an acceleration, or a velocity. But for the engineers, it's a response spectrum. And so what is a response spectrum? Well, it's the elastic response spectrum is what provides a link between seismologist and earthquake engineering practice, as it summarizes the peak response of all possible linear single degree of freedom systems to a particular component of ground motion. So this is what we work with. We take from our database of ground motions, we transform them in elastic responses, and then we build ground motion models. Here I'm showing you a ground motion model, very simple, based on just a function of the magnitude of the event and the distance and the site. Today, ground motion models can be much more complex than this, but this is an issue for another lesson, not given by me, but by some specialist of ground motion modeling. But for sure, the concept is the same. You have a strong motion database, you compute the spectral response of each of them, and then you try to find the parameters that fit this equation. And then you're ready to go. If your scenario is a 6.5 at 20 kilometers depth, well, this ground motion model of 2003 will give you this spectral response. So now this is for one value. What we do is we do it for all the possible values, propagating the weight associated with them. And this is the outcome of that propagation of uncertainty for just one event. If we do it for the second event, we can do the same operation. We have, of course, a different distribution because it's not the same magnitude and distance. And then what we do is we combine the two. And this is our way of evaluating confidence levels of deterministic seismic hazard spectrums. And this is what we use to try to analyze the seismic hazard that comes from the nuclear operators, basically in a very sort of synthesized manner. But what I've shown you so far is just one ground motion prediction equation, one source zone hypothesis, and yet we already have a fair amount of epistemic uncertainty. But in reality, we also need to propagate uncertainties due to seismic source zone models. This is also from the Belgian study. As you can see, of course, geologists don't necessarily agree about how to frame these zones. You could have also regional attenuation differences. What I've shown you is sort of a mixture of regional and national attenuation models. But here, for example, at 100-kilometer distance, if you're in the Alps, you will only, for a magnitude 5 or 10 kilometers, you will only have a sort of intensity 3, whereas in the Armorican Massif in the north, you could have an intensity 4. Just so there are regional differences, but they're very difficult to capture when computing earthquake capital. And so finally, of course, there is a very big uncertainty, epistemic uncertainty, due to ground motion models. What I'm showing on the left is the number of ground motion models that are produced every year, and it's increasing. And the spread of ground motion models for a given magnitude scenario, it still remains pretty wide. So it's probably important to consider this epistemic uncertainty as well. Although today in the nuclear regulation, it's only the red curve that is considered. So my takeaway message is that we can propagate uncertainties in the SHA, and we should. We should consider different seismic source zones, different intensity models, and ground motion models. So thank you for your attention. And for more in-depth discussion on methodological developments at IRSN, I have provided you two papers that you can read on if you're interested, or if you want to discuss. I'm available for discussion. And with this, I think I will leave it to Céline, unless you have.
Yeah, maybe we can stop for questions at this stage. So if anybody has questions or again comments. So, just to make clear, what you do is that so only earthquakes that have been known to occur are considered, but then you assume that they can occur as close as can be from your
Exactly.
site. Yeah.
Yes, exactly. This is the fundamental of any deterministic approach is that.
Okay, so it's a very conservative way of dealing with the hazard, because I mean you have your earthquake just underneath your feet. Yeah.
Well, it's conservative in most cases where the seismicity is low, for sure.
Yeah.
Conservative with respect to probabilistic approaches.
Mm-hmm.
But when you go even to the Alps or the East, in higher moderate seismicity regions, and you do a full PSHA, and you propagate also the uncertainty, here, due to ground motion models, that we ignore, then you can have a probabilistic seismic hazard that can lead to higher values than the deterministic hazard.
Hmm.
Because the uncertainty due to ground motion models is actually quite big, and in probabilistic models that's integrated, whereas here we are ignoring it.
Okay, questions, anybody?
I have one.
Yeah.
I just want to know how common is the inclusion of paleoseismological information in this kind of models, because usually we know it's really common, but how common is it in reality actually?
Well, no,
Thank you.
it's not a question of being common. It's in the regulation. I didn't go through the details of the regulation, but the regulation says that if your site is in the vicinity of a paleoseismological evidence, then you have to consider it. And so we have something like 4 or 5 sites where we have to consider it. The way to consider it is always under debate, but basically, well, you have to estimate the magnitude of that paleo earthquake, of course, and that's usually quite challenging. But then we do consider it. If we have evidence, we plug it in. Again, just a scenario like this, and no uncertainty on ground motion models, just a median ground motion prediction. Well, that's why paleoseismology in France is a difficult task, but when a result comes out, we are obliged by the regulation to take it into account.
Thank you.
Thank you, Don.
So there is a question on the chat.
Oh, on the chat. Hello, I would like to ask, what is the distance limit to consider an event in the vicinity to a site? I don't know who is asking this question. Maybe I should. There is no limit. The limit is mainly given by the ground motion model. Usually, we cannot go very far with this model, for example, not beyond 100 kilometers. But I mean, if the site, we have a site, a seismic zone in. Oh, I'm blocked here. I cannot do anything. See.
No, yeah, it's moving.
No, c'est bon. C'est bon, c'est bon. Like, let's say that if my site of interest was all the way to the west of zone 2, I still have to consider a strong event. If a strong event were in the zone 1, then I still have to consider it all the way, as long as the ground motion prediction model allows me to take it into account.
So it's about 100 kilometers.
For this ground motion model, yes. Today we can go a little bit beyond. Like Jared showed, he went 300 kilometers away. It's a ground motion model dependent in terms of you need to know in your database what did you use to predict your model. Here I don't have. Yeah, I have the distances here. So you see, we have some around 100 kilometers. We don't have much data anymore. So it's you're not predicting, you're extrapolating beyond that distance.
I have a somewhat personal question for you, Oona. I mean, I don't live that far away from the Beauval nuclear plant. So just to make sure, do you actually, because I mean, the regulation tells you that you are, I mean, you have to do this type of approach, but do you also compare to PSHA for all the sites just to make sure that
Yeah. We've made it's not obligatory because the nuclear authority has a hard time understanding how PSHA works. It's not intuitive. So, but we do it. We do it, and we did it for the post-Fukushima Grand Carénage. Maybe you heard about it. So yes, we do consider it. And for Bouger, I don't have it in mind whether it's stronger or not, but it's close. It's close. Bouger is in a higher seismicity region.
Yeah, yeah.
So then we have a little bit of additional discussion with the operator and the safety authority.
Hmm.
But I'll let you know.
Right. Okay, I'll let you know if I can predict one earthquake here also.
Oh, I forgot to say, we cannot predict earthquakes. We're just here to try to make sure that if an earthquake occurs,
Yeah.
well, we were good enough that nothing will happen to the nuclear plant.
Okay, questions, anybody? Okay, so maybe we can move on. Thanks a lot, Oona. Maybe we can move on to Céline.
Yeah. So, David, I have to leave exactly at maximum 5:45. Huh? So I try not to be too long.
Yeah, yeah, that should be okay.
I'm obliged, no way.
Yeah.
Alors. I don't know why I have two of them. Okay, should be this one. It doesn't work. What do you see?
A black screen so far.
Alors,
Le
oui,
même
it's
problème,
not working.
t'as 2 écrans?
Ça va être. Oui, but it should be okay. It
Oui.
doesn't work.
Yeah.
Ouais, c'est bon, c'est bon.
What do you see?
Well,
A lot of
see your
different
screen,
windows,
the
but
whole
yeah, the
screen.
full screen at the
You see
moment.
my whole screen?
Yeah.
Yeah, so if you move on to
Allez,
diaporama.
no, so this is not good. Okay.
Okay.
So you know what? I was at home, everything was working. And 15 minutes before this, my whole street has lost the electricity. So I came here rushing.
Okay.
I'm not started very badly. Alors, let me know now.
Still searching for something. It's still black.
Ouais, okay. So it was working super fine at home and now it's not working.
Ah ouais,
Alors, I don't know why. How do I do that? Shit.
Tu fais comme moi, tu le mets sur un écran.
Alors,
Okay.
okay. This is strange because, okay, yeah. Let's do it differently. Okay. Okay, I start again and you tell me.
Yeah.
C'est bon.
Yeah.
So how is it now?
Ben, on est sur la page.
Bon, on voit tes diapos sur la gauche là, mais c'est pas gênant. Ah,
C'est
c'est
bon.
parfait.
C'est
Yeah,
parfait.
perfect.
Well, okay, so I have only one screen. I just increased the. You hear me?
Oui, oui.
Yes.
Okay, so my idea in this presentation is and now I cannot pass the. Ah ouais, mais ça it doesn't work. I cannot change the. There is something strange because it didn't work with Oona.
Yeah, well,
And now it's not. I am blocked. I cannot change the.
okay.
Completely
Even
blocked.
with the,
Alors, so I
okay.
can't. C'est quand même super bizarre. Hein. Comment je fais ça? Peut-être je vais partager, mais je vais faire comme Oona. Je peux pas. I can't put it in full screen, in fact.
Yeah, but it's okay.
Mais non, mais ça va pas ça. Or I stay like that.
Yeah, you can stay like this. I mean, it's okay. Yeah.
Ok. On va y arriver. So the idea in this presentation is to do after a short introduction. The idea is to introduce earthquake catalogs and then present an example of a full PSHA study with an illustration in Ecuador. And then I wanted to address very shortly some challenges related to the testing of PSHA against observations. Okay, so short introduction. The seismic hazard curve is the main outcome of a PSHA study. It delivers at a given site annual exceedance rates for a series of acceleration levels. And once the hazard curve is determined, it can be interpolated for any return period of interest. For example, 475 years, which is often used until now in building codes. And the inverse of the return period is the rate. So if you want to estimate PSHA for a site, so let's say, for example, for the city of Quito in Ecuador, you need a source model that defines all earthquakes able to produce ground motions of engineering significance in the city. And you also need a ground motion model that predicts the ground motions that these earthquakes will produce in Quito. So among the earthquakes posing a threat, let's consider, to begin with, these two events, a magnitude 8.2 on the subduction megathrust occurring on average every 800 years, and a magnitude 6 on the Quito fault just beneath the city. So here are the PDF probability density functions for the acceleration generated in Quito. The accelerations expected from the Quito fault are much higher than the accelerations expected from the subduction event, as this fault is much closer. So from these distributions, it's straightforward to calculate ground motion exceedance probabilities. And then for each earthquake, it's straightforward to calculate the probability of exceedance by multiplying the frequency. No, its frequency is multiplied to its probability of exceeding different acceleration levels to get annual exceedance rates of the series of acceleration levels in Quito. The exceedance rates related to the magnitude 6 earthquake are larger than the rates related to the subduction event. So the hazard curve in blue is obtained by summing the contributions from all events able to generate ground motion in Quito, these two events plus all other events. Okay, so now I have a few slides on earthquake catalogs. Earthquake catalogs are what we know about the past, and they represent a primary information for assessing hazard. So to evaluate seismic hazard, the catalog must be as long as possible to be representative of the seismicity in the region. For every region in the world, there is always an instrumental part beginning in the 60s with a rather low magnitude of completeness and quite precise earthquake parameters. And then there is an early instrumental period from 1900 to the 60s, characterized by a rather high magnitude of completeness and most often significant uncertainties on earthquake parameters. And then to extend the window back in time, historical seismicity is usually available with earthquakes parameters inferred from macroseismic data. And then the only way to extend back in time the time window is through paleoseismic studies or archaeoseismicity also, and paleoseismicity if available on faults. So these different data sets must be merged to build the earthquake catalog for seismic hazard assessment. In the instrumental part, which is here illustrated in Ecuador, so the work usually consists in gathering earthquake solutions from different catalogs, global ones, local ones, and for each earthquake, a solution must be selected among the solutions available. The earthquakes are always characterized by different magnitude types, and conversion equations are always needed to convert these magnitudes into a unique definition of magnitude, which usually is the moment magnitude. And all these steps, they bear large uncertainties. So as for the historical part, the work usually consists in inferring earthquake parameters from macroseismic data. So here is an illustration in Ecuador for an earthquake that occurred in the middle of the 19th century in northern Ecuador. So from the intensity data set, as Oona showed you an illustration in France, the confidence contours have been determined for the location of the epicenter, and the magnitude range has been determined. So the precision of the earthquake parameters estimated strongly depend on the amount of intensity data, as well as the exact distribution in space. I switched to a completely different geographical area, to the Eastern Mediterranean. In the Eastern Mediterranean region, the situation is quite different from South America. There are plenty of existing studies analyzing intensities and proposing earthquake parameters. And for building the earthquake catalog of Lebanon, rather than going back to the intensity data, we made a thorough review of existing studies, and we analyzed the exact data underlying each study, and we established a list of earthquakes described by reliable studies. And I will illustrate the difficulties that we may face on one event that occurred in the middle of the 8th century. And I don't have my, yes, but it doesn't matter if I don't have my animation. So on this map are reported the intensities available for this earthquake. It's an example of a historical earthquake that has very different interpretations. So when you search in the literature, you have part of the studies that consider that it's a huge earthquake that caused destruction from the Egyptian littoral to northeast Syria. And thus, these studies, they associate the earthquake with a very large magnitude. And you have another set of authors who believe that the different dating systems in the ancient texts have created confusion, that all the reports considered should not have been associated to the same earthquake, but at least to these two events, and they associate a much lower magnitude to the 746 earthquake. So it's a typical example of the difficulties one has to face when working with historical data. The uncertainties may be huge. So earthquake catalogs bear large uncertainties, but they represent a primary information for assessing hazard. Earthquakes, future earthquakes may occur where they already occurred, and they may also occur in areas that have been quiet in the history. So the past seismicity information needs to be combined with other data, other measures of the seismic potential of the area. And now my aim is to show an example of a full probabilistic seismic hazard study, and I will describe the work that we did in the past in Ecuador. So Ecuador is a country facing a high seismic activity and has experienced destructive earthquakes both on the subduction interface and on the crustal shallow faults. You have the Nazca plate, so the subducting beneath the South American plate at a rate of 50 to 60 millimeter per year. And you see the North Andean block that moves towards the northeast, with most of the deformation accommodated along this corridor here of transpressive and strike slip faults. So to build the hazard model, we gathered a team of experts in seismology, in geology, and in geodesy. And the first step to evaluate hazard is to build a source model that describes all earthquakes that may occur in the future. So we propose a segmentation for the subduction interface based on the ruptures of past megathrust earthquakes, as well as on available interseismic coupling maps. To account for shallow seismicity, we've been working with areas enclosing the main fault systems that have been defined. Intraslab seismicity was also accounted for. At that time, we've been using dipping volumes because of the large uncertainties on the depth of the earthquakes, as well as the uncertainty on where exactly is located the slab. So once the source zones are defined, most often the earthquake catalog is used to model the recurrence, and the recurrence is usually established from the moderate magnitude range, okay, magnitude 5 to 6, 6.5, and then extrapolated up to a maximum magnitude. So in this study, we had decided to take into account the uncertainty on the building of the earthquake catalog, and so we used 3 alternative catalogs based on 3 different strategies of merging and homogenizing seismic data sets. So you have 2 examples for Loja, one of the interface sources, and Esmeraldas, another interface sources. So for some sources, the catalogs led to similar models. And for other sources, the 3 earthquake catalogs, they led to quite different seismic rates that we decided to propagate. We decided to keep this uncertainty, quantify it, and propagate it up to the final results. So to evaluate hazard, we need a source model, and we need to combine this source model with a ground motion model. So a ground motion model can be established for a region when you have a lot of strong motion recordings. In Ecuador, the strong motion stations had been installed rather recently. And at the time of the study, there wasn't a proper database to work with. So we needed to import models. And as an attempt to capture the epistemic uncertainty on the prediction of ground motions, for each earthquake type, we selected 3 alternative models relying on different databases. So to predict ground motions generated by subduction events, we selected the most recent at that time global model, as well as a model from Chile and one from Japan. And we compared the predictions of these models here on this figure with the recordings from the 2016 7.8 subduction event that struck the northern coast of Ecuador in 2016. And as shown on this figure, acceleration versus distance to the rupture plane, at least for this event and its 2 largest aftershocks, the models were satisfactorily predicting the recorded amplitudes. So as for shallow crustal earthquakes, comparison with observations was not possible, and we have selected 3 models based on 3 different databases. Again, one global, and another one relying mostly on recordings from Europe and the Middle East, and the last one relying mostly on Japanese data. So then, to evaluate hazard, the source model must be combined with a ground motion model, the ones that I just described, and then you can calculate hazard. So this hazard map, these 3 maps, they correspond to a return period of 475 years. The acceleration that is mapped is the acceleration that has a 10% probability of being exceeded in the next 50 years. We considered 3 alternative earthquake catalogs, so we get 3 alternative hazard maps, and we show that indeed the uncertainty on the earthquake catalog may impact strongly the hazard estimates, as for example, here on the northern coast of Ecuador. And from these 3 alternative hazard maps, you can also produce a mean map. So we get hazard values larger than 0.3 G on most parts of the country and highest values along the northern coast. So this area model relies heavily on the earthquake catalog. And we observe that in 2 regions, one close to the border with Colombia and one south of the city of Guayaquil, here, the acceleration values were rather low, although there are some active faults clearly identified with deformation that has been measured both by geology and geodesy. And these areas, they've been seismically rather quiet in the instrumental period. So we decided to develop a fault model and use the information from active tectonics to define a set of simplified faults. So you recognize here in orange and red the corridor of faults accommodating the movement of the North Andean block or North Andean sliver with respect to South America, the South American plate. So the description of these faults bear large uncertainties, uncertainty on the exact trace of the fault, uncertainty on the extension at depth, on the average slip rate on the fault. And on top of that, a major assumption is made that most of the deformation is accommodated along these exact fault segments. Oops, this is my phone. Okay, so for each of these faults, how do we estimate earthquake frequencies? We use the slip rate. So we combine the slip rate with the surface of the fault to determine the total moment rate deficit accumulating on the fault. And then this moment rate deficit is converted into earthquake frequencies. And in this study, we choose the Gutenberg-Richter model as a magnitude frequency distribution. So assuming a B value and a maximum magnitude on the fault, so what could be the maximum earthquake this fault could generate, the moment balance recurrence model here is fully determined. So including faults, and in this case, crustal faults into the model, we obtain hazard values larger than 0.5, 0.6 along the transpressive corridor, accommodating the movement of the North Andean block to the northeast. So now we have, at that time in this study, we had 2 main models, one based on area sources, enclosing the major fault systems, and one integrating faults, and both bear large uncertainties. And these uncertainties, we believe, are representative of the knowledge at the time we build the model. So we included both models in a logic tree. And in the area model, we decided to account for alternative earthquake catalogs, whereas in the fault model, we decided to take into account the different assumptions we had at that time on the seismic component of the deformation. And then combining this source model logic tree with the ground motion logic tree, we obtained a distribution of seismic hazard estimates, which are representative of our knowledge at the time we built these models. So we obtained a distribution of seismic hazard maps, more than 300. And here are displayed the mean and the percentile 16th and 84th. So the uncertainties on the source model and on the ground motion model have been propagated up to the hazard estimates. So the idea in Ecuador and elsewhere is that these hazard maps may be used by the Ecuadorian authorities to update the building code. Our responsibility as scientists is to deliver hazard map representing the best our knowledge, and then it's the responsibility of the authorities to select the exact hazard levels that will go into the regulation. Okay, most important for us, scientists, was to identify what parameters are responsible for the largest uncertainties on hazard. So here, hazard results are displayed for 3 cities, Guayaquil, Esmeraldas, and Quito. In black, the total distribution for the acceleration at 475 years return period, and in red, the distribution considering only the ground motion model variability, and in blue, the distribution considering only the source model variability. So we show that for some sites, like the coastal city Esmeraldas, the uncertainty on the source model controls the overall variability, whereas for other sites, like Guayaquil, it's the uncertainty on the ground motion model that controls the overall variability on hazard. So if we want to improve seismic hazard assessment in Ecuador after this study, we know that we have to work both on the source model and on the ground motion model. Okay, I checked the time. Yeah. Okay, so now I take a few minutes to address another topic, which is the testing of PSHA, the comparison of hazard outputs with observations. So seismic hazard models, they are made to predict ground motion occurrences. We do forecast, we build forecasts, and but can these forecasts or predictions, you can use it both terms, be tested against observations? So the most straightforward test of the prediction would be to consider the recordings at an instrumented site. So here I show the data available at a station called, installed in a city called Digne in the middle of the French Alps. So it's the ground motions recorded at the station during a 20-year period, magnitude and epicentral distance with respect to the station. And from this data set, it's possible to build an empirical hazard curve. So you have annual accident rates versus acceleration levels. And so with a 20 years time window, the lowest annual rate that you can get is 0.05 per year. So the accident rates of interest for seismic design and building codes are much lower. They are usually lower or equal to 0.002, which is the inverse of 475 years. So to fill in this part of the curve, an empirical, and to build an empirical hazard curve, we would need a much longer observation time window. And given the time windows available for strong motion station, it's currently not possible to compare forecasts and observations at a given site. So we need to go back. Maybe it can be interesting to spend 20 seconds on what's the meaning of a ground motion with a mean return period of 475 years. So it's a ground motion that occurs on average once every 475 years. So the model always, nearly 99% of the times, the model assumes that ground motion occurrences follow a Poisson process, which means that if at a site we had 100 observation time windows of 475 years available, you hear me?
Yes, 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 yes.
Okay. So if at a site we had 100 observation time windows of 475 years, if we had them, 37 of them wouldn't have seen any occurrence, and 37 of these time windows would have seen one occurrence. So this is a way to say that ground motions of reference in earthquake engineering can be considered as rather rare events. And this is true whatever the site, in low seismicity or in active regions. So the test cannot be performed at a given site, but it can be performed at the scale of a whole network. So here, for example, at the scale of the French accelerometric network. And the idea is to compensate the short time windows by sampling in space. So the model can only be tested as a whole at the scale of the network. In this example, for a series of acceleration levels, we compare the predicted distribution for the number of sites. So what we calculate is predicted number of sites with exceedance in black with respect to the observed number in red. And in this case, at that time, we were comparing observations with the previous European hazard model, the one that is called ESHM 13. The new one is ESHM 20. So we got observations compatible with the forecasted distribution. However, as you can see, the comparison was meaningful only for very low acceleration levels, lower than 0.05 G, because for larger levels, the numbers involved were too small. The time window of observation were still too short. So we also compared these observations with other forecasts. So for example, this in blue, it's a model that was derived during the revision of the actual French building code. And observations where you can see that observations, they were still within the bounds of the forecasted distribution, except for this very low level that is so low that it becomes difficult to ensure completeness of observations. So with simple Poisson simulations that I illustrate here, it's possible to grasp part of the problem. So here I consider a Poisson process that occurs with an annual rate of 0.2 per year. So it means one occurrence every 5 years on average. The model predicts 0.1 per year, so half the true rate. It's underestimating the true rate. If you use basic Poisson simulations, you get the distribution for the number of occurrences on a time window of 10 years here. You can obtain what would be the model distribution and the true distribution. And you can see that only with 10 years, they both overlap. So it's very unlikely that an observation over a 10-year period can reveal an inconsistency with the model. So then if you do the same, but you consider a longer time window, so for example, time windows of 20 or 40 years, the distributions, they still overlap. However, if you go up to 100 years, the overlap is reduced and the observation will have more chance to reveal an inconsistency with the model. So 100 years in that case corresponds to a time window which is 10 times larger than the return period. So with time windows equal to the return period or just twice the return period, the difference between the true rate and the modeled rate has to be huge for the observation to be able to reveal inconsistencies. Okay, so I think I've been quite quick, but it's 5:38, so I'm on time. So with this presentation, my idea was to convey two messages. First one is that the establishment of a source model for PSHA is a huge challenge. And the source model is made to include all earthquakes that may occur in the future with associated probabilities of occurrence. That the uncertainties on earthquake occurrence rates, if accounted for fairly, may have a strong impact on hazard levels. So any research field able to provide insights on earthquake occurrence should contribute to this task, and that we source models, we should have the same level of requirement in terms of uncertainty quantification as the ground motion models have. And conclusion about testing hazard forecast on the few slides I show is that it has to be done, but what we can do is limited because of the comparison between the written periods involved and the actual observation time windows that we have, and we can only test partially the forecast obtained. Okay, I'm done. Thank you.
Thanks, Céline. So we have a very limited time for questions.
Yeah, I'm sorry. Yeah, I have 5 minutes left.
Okay, so please raise your hands.
And I don't see you anymore, but it's the screen anyway.
Yeah. There don't seem to be too many questions.
Question. I was wondering, where is this 475-year period based on? It seems a bit arbitrary, maybe, to me.
Wait, but it is, in fact, it's I choose to provide illustrations for this 10% over 50 years because it's used a lot, but I could show, once you have a hazard model, you can show results for any probability of exceedance over any future time window. Okay, I could really show 2% in the next 100 years. 2% in 50 years, if you consider the Poisson model, which means that acceleration occurrences are random. So 10% over 50 years is equivalent to a mean return period of 475 years. And so you have to relate this 10% of exceedance over 50 years with 475. So this is where the 475 magic number comes from. And I think 10% over 50 years, you have to go back to economic considerations. Why it has been chosen a lot. It was a lot reference ground motion with 10% exceedance over the next 50 years that has been considered a lot for the building codes. But if you go to IRSN for the nuclear power plants, Oona can say something, but they will consider much lower probabilities.
Yeah, well, the 50 years, I think, comes from the States where on
Right.
average, a building,
Yeah.
the life of a building is 50 years. And the 10% is more, from the economics. This is what the society is able to deal with in terms of risk. So, but you're right, you're perfectly right. The big discussion is why 475?
But nowadays it's for 475, 2,475. It's
it's open.
So we build a hazard model, and then we can deliver results for not any written periods. The model is when the model is not made for a nuclear power plant, we should not deliver results up to 20,000 years, but it's it's evolving. In fact, 475 years maybe has been the written period, the one most used, but it's changing. It depends on it's country per country, I think.
Okay. Other questions?
Sorry?
Other questions in any case? I have a short question. I don't know if you have time, Céline. For Equator, so you show that if you consider a fault model for, I can't remember the name of the main fault that cross the country, the crustal fault. So that really changed the model in the end. So I'm wondering, why I mean, is the model so much changed that because the fault wasn't active, and you are considering a catalog with basically, you know, too few earthquakes?
No, it was the hazard is already high. The hazard just with the area model, area closing fault system, it's already high. So it's even higher. That's true.
Okay.
But
All
it's like 0.3 G at 475 years return period, or 0.4 as we were, is already high. Okay. But if we it's I think it's the
on the
tip
map that, yeah, because on the maps that you showed, it seemed to me that it was, you know, much higher the risk than the hazard. I mean, yeah.
You see, it's 0.4 is already quite high. No, but it changes a lot for the sites which are along this fault segment.
Yeah.
Yes, for sure.
So that implies that I mean, the information you used for the area model basically wasn't sufficiently sampling, you know, the activity on the fault.
But it depends on what you believe. Right? Because you may have people who will think also that you need to believe in the slip rate estimated. You need to believe in your assumption about if part of the deformation is seismic or not. You need to the assumption that you make on the depth, the extension at depth of the fault. So there are many assumptions. So yeah, the truth is in between models, I think. Yeah.
All right.
Can I ask you just one question? You have to go. Is
Ouais.
it the depth of historical earthquakes? How do you decide?
Alors so in you mean for Ecuador?
Yeah.
So when we were working on this data set in Ecuador, we didn't believe we could discriminate the depths. So we were looking for the magnitude, the location for a fixed depth, like 10 kilometers, because they are crustal events. It's it seemed quite impossible to also constrain the depth.
Okay. So what's the seismogenic depth in Ecuador?
But it depends but this is a big question. It can be seismogenic, you mean, and then I have to go. You mean
in the crustal region?
But here I think in that model it's mountainous, it's the Cordillera. So I think we put maybe 20-25 kilometers at that time. Right.
Yeah. Okay. Oh, thank you, Céline.
Yeah, thanks a lot, Céline. Okay, you can.
Sorry.
Yeah.
I have to go. I have a child which will be alone in the street in 13 minutes. Okay?
Ciao.
Bye-bye.
Ciao.
Thanks, Céline.
Yeah. Okay, thanks a lot, everybody, for attending the lecture. So actually, the next one is in 2 weeks' time, and I can't remember who's on. Let me check.
Tu peux arrêter l'enregistrement?
Oui, tu peux. Oh, Alessandro.